Will, are you a Lowe's guy or a Home Depot guy?
Home Depot.
Home Depot. So Will goes to
I got all
Home...
my Eagle Project stuff at Lowe's because they cut the wood for me.
Dang it, Will. I guess you got to go where it's convenient, right? But if you're getting a new stove, you go to Home Depot, right? Because you're spending a lot of money. So I'm going to say that we want to add heat to some ice. You're going to put ice on a stove, and what do you got, one of those electric things?
Yeah, I guess so.
Okay, so it's coming in here, and it's like this coil, and somehow it's coming back out here. And
No,
you're gonna...
not that one, like the flat.
Oh, the really fancy one. So that's just that under a plate of glass or
Yeah.
something. And then you put a pot here, and inside of that pot you have a little bit of ice. And the ice is cold, and it's just sitting there. And you add heat to it, and you add heat to it steadily. I guess if you wanted to know how much heat you're adding, like the rate of heat adding, that would be power, and it'd probably be I squared R because it's electrical heating, right? Joule heating.
I don't remember that.
Yeah, you do. So I'm going to add heat linearly to it. I'm going to have the stove on a certain level. It's already heated up. I place the ice on there, and I watch what happens to the temperature of what's in this thing. And I probably want to put a lid on it because stuff's going to get very interesting. I'll say I've got a purple lid, and it looks like a tower or something. So there's my lid. And I'm going to take the temperature when it is ice, and it's going to start down below 0. And that's okay. So here we go. Do you want to start with blue? Is that what you want? I can't do red because it's not steam yet. All right, so it's starting with blue, and I find that the substance heats up, and it heats up rather quickly. And then at a point right here, it stops heating up, and it just... Wait a second. Am I adding heat to it? What's going on? Am I adding heat to it at all? What the heck? Right? It's not changing temperature, yet I am definitely adding heat. When does that happen? Will, what's the temperature?
0.
Ooh, 0 degrees Celsius. Yeah, because it is doing what? What's the ice doing right there?
I meant to say 32.
Shut up. The temperature, what's the temperature right here? 0 degrees. And what's happening to this ice? While this bar is horizontal.
It's melting.
Sucker right here is melting. So I'm going to put an arrow right there and say melting.
But that's water.
Yeah. Yeah, it's general. It's general. Generally, I'd have to use the word, what would I want to use? Liquefying? Liquefying. Sure, yeah, I'd be liquefying this material if I were going to be general as I go that direction. And then I find that all of a sudden, it begins to heat up again. What do I have then?
Wait, what's going on?
Well, see, what happened is I was putting steadily heat into it, and I noticed the temperature stopped changing.
Oh, right, now it's water heating
Now
up.
it's water heating up. Oh, what's up with the slopes here? Are those slopes supposed to be different?
Yeah.
The slopes probably have something to do with heat capacity, and we'll talk about that in a little bit. But I'm noticing I'm putting heat into it, and then suddenly, it stops changing temperature again. And this time, it stops changing temperature for an extremely long time. It's going to run into the stove. Careful, look out for the stove. Yeah, it runs, oh my gosh, look at that. And then suddenly, it starts changing temperature again. What was going on during this time right here?
It's boiling?
Yeah, we would call that, let's use red, right? You're saying that it's boiling here, and what's the general word that I could use for for any general fluid, not just water?
General patent.
No, I think I'm going to call it evaporating.
No, it was vaporizing.
Mm-hmm.
That's what you called it before.
You could also call it vaporizing. That's what you do to aliens if you got a really cool zapper, right? Then, what temperature was that? Where water, in particular, would be doing this boiling, evaporating, vaporizing thing?
100.
Mm-hmm. That is 100 degrees Celsius. All right, super. So we've got melting and liquefying happening right here, and vaporizing or evaporating or boiling happening right here. Notice that when there's a phase change, there's no temperature change. And the amount of heat that's right here, this amount of heat, that amount of heat, Q, I'm going to call it Q liquefying. Can I call it Q sub L? Is that what our book does? I don't even know what our book does. I'm not even on the right chapter here. What do you want to call it? Q sub L, Will? What do you want?
That works.
All right.
Yeah.
Oh, they call it L sub F. They call it the heat of fusion. So that would be if we're going the other direction. Oh, I could cool it down. You bet I could. And I'd get the same pattern. So this would be fusion or solidification. There are so many cool words for this. Solidification. Or we could say freezing. Right? Right, Will? Are you still there?
Oh, yeah.
Okay, so this is the heat of fusion, and it's going to be the mass times, well, however much ice we decided to put in there, the mass times the heat of fusion of the ice. So that's the heat of fusion, and I guess it would take that much heat to get it from ice to water, and it would have to, I guess it'd have to release that much heat to go from water to ice if we're going this direction, in the direction of fusion or solidification or freezing and all that stuff. And this heat right here, this amount of heat that it takes to entirely boil, we're going to call that the heat of vaporization, and it is the mass of liquid that we're trying to boil times the heat of vaporization. And that's a look-upable number. What do you want these numbers? I guess I can give you these numbers. What are they? Something like this guy right here, the heat of fusion is 3. Oh, why is it L? It's called the latent heat. Like a heat that you can't see. Sort of sneaky, right?
We already talked about it.
3.3. Yeah, okay, so I shouldn't even say that, right? 3.35 times 10 to the 5th joules per kilogram. And if I had 1 kilogram, it would take that much energy. That's a lot of energy. You know how many apples 1 meter high up you'd have to drop on a kilogram of ice to melt it entirely?
Like 10.
No. How about 335,000 apples?
That makes more sense
That's-
based on what you have written down there.
Yeah, than 10. Right, good point. So this is an even bigger number. In this one, you'd need 2.26 times 10 to the 6th joules for a kilogram of water to boil completely, to evaporate entirely. Now, what about these slopes? You notice that this slope is really steep, and this slope is really steep, and this slope is not as steep. This implies that water takes more energy to heat up a degree than ice does. And also, water requires more energy to heat up a degree than steam does. This is steam over here, isn't it?
Yeah.
Yeah, let's label these phases. We got steam here, and here we've got water, and here we've got ice. And in between water and ice, I've got some water and some ice. And I guess it's a ratio. It's changing from one form to the other in a linear fashion during this time. And from water to steam, it's changing between the phases in a linear fashion. Should we get another arrow over here? What do I want to do? Put an arrow right here and say if I'm going the other direction, I'm condensing. Yeah, we could call it condensing. Yeah, absolutely. I guess the only thing that I want to add is this little discussion that we were having about this slope. So the slope of this line right here. The slope is the rise over the run, and the rise is going to be delta T. Okay, and the run, well, the run is going to be the heat added, so I'm going to just call that Q. But I've got this other equation over here that says that Q is equal to MC delta T, or as we call it, MCAT. And I can solve this sucker, wait a second, I can solve this sucker for delta T over Q, couldn't I? This says that delta T over Q, ooh, can I do all that math?
If you want.
It's 1 over MC. So I can identify that as the slope. Interestingly, if I have a fixed mass right here, then the slope, if I have 1 kilogram of ice that I started with, then the slope is the inverse of the heat capacity. Does that make sense? That you get a bigger slope if you have a smaller heat capacity?
Yeah.
And a smaller slope if you have a bigger heat capacity?
Oh, you want to? Yeah.
Do you have it, yeah?
Yeah.